Hello friend, my name is Ichekpe Miracle, and in this video I will be discussing on the magnetic effect of the electric current. In physics, the magnetic effect of the electric current. So, as you can see, the magnetic effect of the electric current, the magnetic effect, the origin. This means the origin of the magnetic effect. That is how this topic came about, the origin, how it was created, what brought about it. Also, in this lesson, we will discuss the definition of the magnetic effect. We need to know what the magnetic effect means. We need to know how it relates to the electric current. Then also, we will discuss the magnetic field due to a current carrying wire. The magnetic field due to a current carrying wire. Then again, we'll discuss the Maxwell corkscrew rule. We'll discuss the right hand grip rule, and finally we would identify easily these rules that we'll discuss. That is, I will also show you the way to examine, the way to identify, and the way to use the rules we'll learn today in whatever question you find under this topic. All of this we're going to learn in this video. Now, to the origin of the magnetic effect of electric current. The origin of the magnetic effect can be traced back to a scientist by the name Hans Ørsted. In 1820. He was a teacher of physics, and then he was teaching his students about an experiment, and then right in his front, the experiment actually consisted of a magnetic compass which is used presently in finding directions, a magnetic compass and a straight wire. He actually passed current through the wire, and then he discovered that the magnetic compass was deflected because the magnetic compass was connected actually to the straight wire. And so, to something like this is the magnetic compass in this direction, and this is the straight wire. Why this is indicating direction of current. This is a wire. Then if the current is moved in this direction, the magnetic field will be deflected to this direction. So this was the direction of magnetic field, the direction of the magnetic field, while this was the direction of current, upwards, the direction of the current. So when current was passed through the wire, as at then, he discovered that the magnetic compass was deflected towards the left hand side, and that was because it was above the wire. In another case, he did another where the magnetic compass was below the wire. That is, the magnetic compass was under the wire, like this, and then he passed the current in the same direction, and then the magnetic compass was deflected towards the right hand side, so much that this is the direction of the magnetic field when the magnetic compass is under the wire. Here it was under the wire, and here it was above the wire. So this was what led him to the conclusion that actually when you pass current through a straight wire or through a material, mostly a wire, it actually produces a magnetic field. And that is how he realized that the magnetic effect of electric current could bring about a change from electricity into magnetism. So what he did actually led to the foundation and continuation of most of the topics that are actually embedded under the magnetic effect of the electric current. Now we move to find out what the definition of the magnetic field rather is. We want to know what the magnetic effect of the electric current is. Now to the definition of the magnetic effect. The magnetic effect of the electric current, sorry for not putting that there, is the effect produced from the application of current to a wire. This means that when you apply current to a wire, a straight wire, a curved wire, it produces a magnetic field, a magnetic effect. It has a magnetic effect. That is, magnetism is created when electricity is passed. So it is the effect, the result of the application of current to a wire. It also said that it is the result produced when current, when current is passed through a straight wire. Something like this. When you pass current through a straight wire, like this, it produces a magnetic field around itself, and so we'll deal more with that on the next outline. The magnetic field due to a current carrying wire. The magnetic field due to a current carrying wire. Magnetic field due to a current carrying wire. Now this outline is actually an experiment which you could do on your own. Now we know that a wire is actually in a straight form like this. Sometimes could be thick, sometimes could be thin, depending on what structure of wire or what you want to use that wire for. Now wires actually are meant to carry current, or meant to allow current to pass through them, which means they are like conductors as well. So now for a straight conductor, for a straight wire, when current is passed through it, it actually does something surprising. So it does something surprising, like I said, and that's what we want to find out. Now imagine you have wire connections together, connected to a battery or a source of current. This is the sign for battery. Then also connected to a key or switch, and then connected to a rheostat or a variable resistor. Then this is a pad, maybe a wooden pad, just a flat wood, and then this is a straight wire connected to current, a straight wire. Something would happen here, but we need to put something here. We'll put iron fillings or iron nails, iron fillings or iron nails. So when we dispose iron fillings here, and then we let this straight wire pass through the middle of the pad, that is, we pass the wire through the middle of the pad, we notice something. But first of all, we scatter the iron fillings all about the wooden pad. Then we would pass the wire and then connect it to the battery, the key, and the rheostat. Then when the key is switched on, or the switch is on, the current flows, and then up to this point, we notice that as the current passes through the straight wire, the iron nails or iron fillings will be arranged in circles. In concentric circles. And then this is as a result of two rules. The two rules which we are going to discuss soon. The two rules are the Maxwell corkscrew rule, the Maxwell corkscrew rule, the Maxwell's corkscrew rule, and then second is the right hand grip rule. The right hand grip rule. The Maxwell corkscrew rule and then the right hand grip rule. So these two rules will help us explain better the magnetic effect of electric current, that is, the magnetic behavior of the straight wire when current is passed through it. Now we move to the Maxwell corkscrew rule. The Maxwell corkscrew rule. Now, to explain the experiment which we did earlier, I said current was passed through a straight wire. Then we noticed that iron filings that were displaced around the wire were arranged in concentric circles form. Another part of the experiment which I did not mention was when the current was going down as well. But I will use these rules to explain what will happen when the current is going down. Now, we discovered that the current was moving, in this direction. But how do we know where, rather, this is the magnetic field, and this is the current. We noticed the magnetic field was moving in this direction. Now, the current was moving in this direction. The magnetic field is actually a vector field, and so it actually has magnitude and it also have direction. So this was its own direction. Unlike the current is a scalar quantity, but it still indicated it was still passed through a particular direction. So what am I trying to say now? That for a straight wire, when current is passed, it actually displays a magnetic field which we do not see, but we can observe from its behavior. Now, for the Maxwell's corkscrew, it states that if a right-handed corkscrew is turned in the direction of current, it states then that the direction of rotation of the corkscrew will result in the direction of the magnetic field. Now, that may seem a little long. I will rephrase it again. He said if a right-handed corkscrew, this is how a corkscrew looks like. I may not be able to give the proper view, but you could also search it out on the internet. It looks somewhat like this, like a normal screw, but there is the right-handed and there is the left-handed. That is the one that can be turned towards the right hand side, and then the screw that can be turned towards the left hand side. And this is for the point of the screwdrivers, that is where the screwdrivers will come in contact with to rotate that screw. So you say if a right-handed screw is turned in the direction of current, the direction of rotation will result. So this is the other way around. The direction of rotation will give the direction of the magnetic field, like this, something like this, to this direction, when the current is turned, or when the corkscrew is turned in the direction of the current. So the Maxwell corkscrew was created by Maxwell, obviously, and then it was used to explain the direction of current magnetic field when the current is passed in a particular direction. Now, I said I was going to explain what happens when the current moves downward. Now, when the current is moving downward, that is similar to the second experiment from Hans Ørsted investigation. That is the one you saw the one that was above the wire, and then the one that was below the wire. The one that was above the wire was actually when the current is going down. Then the one that was below the wire is actually when the current is going up. Now, it's like this. When the current is going down, here this one was moving in this way. Instead, this one will move the other way around, to move opposite. to the normal one, which means it's somewhat like this, coming from this side, entering this side, coming from this side, then moving into this side. So this is the view of how the magnetic field will be moving when the current is moving downwards. Now we move. I hope you understand the Maxwell corkscrew rule. We move to the direction. We move to the right hand grip rule. That's actually my best rule because you can actually use your hand to simplify and explain that one. Now we move to the right hand grip rule. The right hand grip rule. Listen attentively, please, because this now also relates to the Maxwell corkscrew rule, but they talk about the same thing, but it is different in its own understanding. Now, this is the thumb finger, as we all know. It represents the direction of the current. I'm explaining it. It represents the direction of the current when it is moving upwards. When it is moving upwards, which means that this is the indication for upwards. This is the indication. This is the indication for upwards. So when it is moving upwards, that is the direction of the current. So this actually, our fingers will represent the direction of the magnetic field. The direction of the magnetic field. When the current is moving upwards. Now the right hand rule, or the right hand grip rule, also known as the clenched fist rule, has another name for it, the clenched fist rule, because your fist will be like this. It is clenched. Your fist, the clenched fist rule, or the right hand grip rule. This was just to indicate the direction, the position, and the movement. Now, the clenched fist rule. This now is indicating the direction of magnetic field, like I said before. The right hand grip rule states that if our thumb finger represents the direction of current, then our fingers moving in a concentric, this forward form, each of them are moving, so it's like together you have concentric circles, just like that experiment we had before. So it states that if the current is moving and the thumb finger is representing the direction of the current, of the moving current through the wire, then the fingers which fold or which sweep in the direction to the palm are actually the direction, or indicates the direction of the magnetic field. I'm just paraphrasing it, but the picture and explanation that will come after it now will be explanatory. Now, we remember clearly that the picture was something like this. When the current moved up, we noticed that something was entering like this and coming out like this, entering like this and coming out like this. Concentric circles form. So now this can also explain it. When the current is moving up, this one will go into and come out like this. It goes into and comes out like this. Also, when the current is going down, this may be a little bit uncomfortable, but it's also the other way around. It moves, it's still in concentric circles anyway. Since this one was moving like this one will move back in the opposite direction, because the current is actually in an opposite direction. Here the current is moving downwards, here the current is moving upwards. So the magnetic field is moving into this direction, and now something like this will be from here into look at this finger, focus on this, moving into, which means it came from here into this side, into this side, into this side. While the finger is pointing like this, it comes into this side. I hope you understand that. So now we move to the easy identification of rules. The easy identification of rules, or the representation of rules. Now we've been discussing the magnetic effect. We've not stopped. We are still on it, and we discussed two rules: the Maxwell corkscrew rule and then the right hand grip rule. So now I want to move to the next one. That is, we want to identify these rules. We want to know how we can use these rules easily. You know, the statements for each of those rules, that is, the definitions of each of those rules, are actually long and they can be difficult to remember. So for you to be able to remember these rules, we discovered a way, an explanation for you to, as in a way for you to get each of those rules, and it's something like this. Now we know, or now you have known, that when current is moving up, concentric circles are formed, and then the current that is moving up is actually the direction, actually representing the direction of current, while the concentric circles that are formed in a particular direction that can be identified as well are actually representing the direction of the magnetic field. Now this is still the direction of current. On changing the direction of current upwards, direction of current, you will notice that concentric circles are formed when current is passed. But instead of using concentric circles, we are going to use only one circle to identify this thing. Now when it is moving up, a circle magnetic field or circular magnetic field is created in concentric form. Do not forget that. Do not forget that. So like this, you notice that, okay, let me use the concentric first before I switch to the normal one. So you notice that it's like this. It actually moves in this direction. That is, it enters into this lace and comes out like this. It comes out and enters. Now we will decide to represent anything that enters with this. This is representing the entering, or the enters, yes. Then the exit represented with a common dot, common point. Now what does this mean? I'll use this to explain the work now. When the current is moving up, what do you have? You have the magnetic field moving like this to this side, right? Like this to this side, and then coming out through the other side. Now instead of drawing magnetic or circles, instead of drawing the circles, you can just indicate it by putting something like this. When the current is moving up, you have this on this side and you have it on this side. What this means is, I am entering into, this is for entry, and I am coming out of this place. I am coming, this is for exit. I hope you understand that. When it is moving in, it comes out. That means that all the magnetic fields, all the concentric circles rather, they all follow this method. That is, they enter into this. This is just to represent it, not that it actually appears. They enter into this area and then come out like this, which means instead of drawing your circles, which will be too wobbly and too unclear, you can just put something like this and then something like this. When the current is moving up, the magnetic field comes out of this point into this point, again out of this point into this point. The same thing applies to when the current is moving downwards. You know, when the current is moving downwards, you still have a circle as well, but instead of moving in the normal direction, it moves in the opposite direction. It moves in the opposite direction, which means it comes out of this place and enters. So you can represent it like this. It comes out, will be here. It, enters again. That is, it comes out of here, enters. The concentric circles of the magnetic field will come out and then enter. Come out and start. It will look something like this, somewhat like this. So this is when current is moving up. This is how the magnetic field will be moving. When current is moving down, this is how it will be moving. That is from like this into the side, and from like this into the side. Now we've learned a lot. I'll go back. I'll go through each of those things we've discussed. Now, in summary, we've discussed the magnetic effect of the electric current. We discussed the origin, and where I said that Hans Ørsted, a scientist and a teacher of physics, was doing his experiment in 1820 while teaching his class, and then he was using a magnetic compass and a straight wire. He realized that when the wire was above, rather when the magnetic compass was above the wire, the magnetic field was moving towards the left, and then when it was below, it was moving towards the right. The magnetic field was moving towards the right. Now we also explained the magnetic effect of the electric current, the definition, and I said that it is the process whereby electricity is changed to magnetism, or it is the effect that is produced when electric current is passed through a straight wire. Then thirdly, I explained the magnetic field due to a current carrying wire, where I mentioned an experiment of a rheostat, a key, and a battery, or a source of electromotive force, source of current, that you could connect to a straight wire, and then a pad in the middle or at the center where the straight wire is passed through, and then you displace iron fillings on the pad. You notice that when current is passed through that straight wire, concentric circles will be formed. Concentric circles will be identified because those iron fillings will now form that circle. They will form those circles around the straight wire. So I explained that method. I explained why it was like that using the two rules, the Maxwell corkscrew rule, where I said that if a right-handed corkscrew is turned in the direction of the current, the direction of rotation of the corkscrew, yes, is actually the direction of the magnetic field. That was what I said about the Maxwell corkscrew rule. And because it was a long one, I gave examples on, I simplified it rather on the easy identifications of rules, where I showed you something like this, that when the current is moving up, this will actually be your entry, and this will be your exit. But when the current is moving down like this will be your exit, your entry rather, and this will be the exit of the magnetic field. So all these things here are representing the entry and exit of the magnetic field when it is moving up. This is also representing the current direction, and then the entry and exit of the magnetic field when the current is rather moving downwards. I explained the right hand grip rule. I said the thumb finger represents the direction of the current upwards. That is, this will determine whether it's going up or going down. I also explained that the fingers were the direction of the magnetic field. So now that was all I explained rather on the magnetic effect of the electric current. I hope you enjoyed every bit of this video. Please do hope to subscribe to this channel, Lemap TV, to get more interesting videos. The next topic, which you can see right now, the next video rather, which you can see right now on your screen, will be on the principles of electromagnetic induction. I will be teaching on it, as well as Faraday's law and Lenz's law. Rather, in this channel, we treat mathematics as well, so I'll be taking you through mathematics topics as well, for you to be able to understand every formula, method, and equation involved in your topics.